Hello everyone, I'm Liu Xin, co-founder of VirtualMan. The subject of my presentation today is a novel multi-objective ADMET modeling for structural optimization using reinforcement graph convolutional neural networks. Here is today's outline, including introduction, model explanation, results, conclusion, and we have a demo site available for you. ADMET plays a key role in the pharmaceutical industry, and many drugs fail due to unintended drug-drug interaction or lack of efficacy due to poor drug pharmacokinetics. So far, many tools are available to predict various ADMET properties. So we could use those tools to modify the compound structure for the single endpoint. But in normal situations, while modifying the molecule structure for one ADMET property, another endpoint gets worse. So far, no suitable tools are available to assist the modification of molecule structure for multiple ADMET targets. Then Zhou proposed a reinforcement learning model based on neural networks that enable molecule modification of two objectives, drug likeness and C log P. In our work, we introduced the algorithm to optimize multiple ADMET properties to avoid the situation that molecule modification of one property make another property worse. Reinforcement learning is a subfield of machine learning. We design a scoring mechanism for an environment and let an agent learn how to score higher in such an environment. These actions are selected from an action space. The algorithm is usually used for play games, but when we do drug design, we add or remove something and get better properties. It is like a game. So we apply the model to modify compounds and use it to assist in drug design. Q-learning is an implementation of reinforcement learning that has proved to be capable of solving a lot of problems. Traditional Q-learning consists of a Q table to record the maximum expectation score that can be obtained by performing a certain action in a certain state. Deep Q-learning uses a neural network, deep Q network, instead of traditional Q table. In our work, we use DQN as the reinforcement learning method. We just talked about the agent needing to select an action from the action space in a certain state. Although the action space in the compound modification is not as intuitive as in the game, which is possible to design a way to describe the action space, like up, down, left, right, or A, B. So we need a method to describe the action space of molecule modifications. Here are basic actions to modify molecules. This includes adding an atom, deleting an atom, turn a single bond into a double bond, or a double bond into a triple bond. lowering a triple bond to a double bond or a double bond to a single bond. Change the bonds are synchronized with the deleting or adding the hydrogen atoms in order to maintain the correct balance. In this way, we can turn design compounds into the input of reinforcement learning. Next, we will talk about how to design the environment to give the agent a rating after the action selection. Reinforcement learning is originally used to score states or results by formulas or algorithms as a discriminator. We replace those formula or algorithms with neural networks. Graph convolutional neural networks are used as neural network ADMET discriminator to score the agent. This allows the agent to try to modify the molecule that can predict better results in the ADMET model. Here is a diagram of the graph convolutional neural network architecture we used. We used 77 features to describe an atom, which include atom type, atom number, is it an acceptor, donor, or in an aromatic ring, hybridization, number of the hydrogens it connecting. In addition, we use the top-K algorithm for this gathering layer to convert the graph to an fixed-size vector. Another important thing is the multiple objective. We take the multiple ADMET GCM models that we want to modify and design the reward function so that the compound can be modified with multiple ADMET properties at the same time. This has the advantage of avoiding optimizing an ADMET property and then making another ADMET property worse. In order to validate such an approach, we design an experiment where the goal is to input a molecule and add multiple models as discriminator to achieve multiple objectives. After the optimization of DQN, where we can achieve better molecule in the model prediction of each objective. We choose SIP as an example because SIP contributed 50% of the clearance in top 20 drugs in the US 2002. As an example, our model can change the metabolic pathway of compounds in SIP. We changed a compound from CYP3A4 inhibitor to CYP2D6 inhibitor. It is only necessary to design a reward function with high fraction for low CYP3A4 inhibitor and high fraction of high CYP2D6 inhibitor, so that reinforcement learning can be achieved to modify the molecule of CYP3A4 inhibitor to become the molecule of CYP2D6 inhibitor. We used Pumpkin AID1A51 as the dataset for training the GCM model. This contains data of SIP1A2, SIP3A4, SIP2D6, SIP2D9, SIP2C19 inhibitors. For the example shown here, we use SIP2D6 and SIP3A4 data in the dataset. Consider active compounds in the dataset is AC50, less than 10 micromole in cytochrome assay. The accuracy of GCN models are on the right-hand side. The SIP3A4 is 83.3%, and the model for SIP2D6 is 83%. This is our results. The molecule on the left-hand side is a molecule that was experimentally identified as a 3A4 inhibitor. Our model can produce about 5,000 molecules after a day of modification, with the full results on the right-hand side as example. The model predicted probability for the molecule on the right-hand side are over 80% for 2D6 inhibitor and less than 15% for 3A4 inhibitor. It is feasible to use the ADMET model as a discriminator to help the environment to score the agent. As the results show, this is indeed successful. The ADMET model of the neural network as a discriminator does enable the agent to make model predictions on molecules with better results. It is also possible to modify multiple ADMET properties at the same time so that each property is modified in the desired direction. In the CYP example, it was successful to modify multiple properties at the same time and all in the direction we wanted. The experimental results show that we succeed in modifying a compound by reducing the probability of CYP3A4 inhibitor and increasing the probability of being a 2D6 inhibitor. Similarly, it is possible to modify the molecule to not be a CYP inhibitor at all. The last one is no additional knowledge is required. Only sufficient data sets are needed to implement automatic molecule modification. In this approach, all that is needed is model architecture of neural networks and the data set. No additional human knowledge is needed. In the case of CYP experiment, we only use the dataset of CYP3A4 inhibitor and the CYP2D6 inhibitor to complete the experiment of changing the molecule of CYP3A4 inhibitor to CYP2D6 inhibitor. Such a model can be mixed with other computation methods in the discriminators of the environment. For example, we have tried to use both C-log-P and mutagenicity on this model, where C-log-P is an algorithm and mutagenicity is a neural network model. In addition, the feasibility of synthesis has not yet been considered for the results produced by such model, and future research can be developed in this direction. This is our demo site. You can use the default molecule or enter your own molecule as model input. You can choose either log-P or mutagenicity, or both of them, as the properties you want to modify. The log-P can be either a C-log-P algorithm or a neural network-based log-P model. Because this is a demo site, and we calculate the modification in real time, we limit the number of steps of reinforcement learning, so the results are faster but fewer. The original reinforcement learning typically produces thousands of compounds that meet expectations. This demo is open to everyone, so you can try it out. Here is the website and email. If you have more requests, please contact us through our website or email. This is the end of my presentation. Thank you for your attention.